All right. Welcome, everybody. Hope you all had a good day yesterday. Today, we're going to be diving deep into comparative effectiveness analysis designs. So we've got a day today to try to go from wherever your current level of understanding is through all of us all having shared understanding and ability to design and execute a study following OHDSI best practices. I am Patrick Ryan. We have 4 faculty members here today. We've got Christophe Lambert from the University of Mexico, Marc Suchard from UCLA, and Martijn Schuemie from Janssen R&D. So we're going to be your hosts for today, walking you through all of the material. And I get to go first to kick this off. Just to orient you guys to what we are going to be doing today, the agenda, which I think you should have received as an email. So I'm going to start with just an overview of the new user cohort design and talk about kind of the principles of propensity scores and how we're using that to do outcome modeling. We then sent you guys a homework assignment, which was to read a paper by David Graham et al. Did everybody receive the email homework? Yeah. How many read the paper? All right. How many are lying? Okay. Well, we give out the homework. We're actually going to make use of all of that material today. And actually, Christophe's going to lead you through an exercise where we're going to really think as a group about what's good and what might be different about that study than otherwise we'd like to do. From there, we're going to take a break. And then Martijn and I are going to walk you through how to implement a cohort study using the OHDSI tools, both through the design phase as well as the implementation using the R packages that Marc and Martijn have developed. Then we're going to take a lunch break. We've got lunch somewhere here. And then in the afternoon, we're going to, after we've given you a presentation of how to do it, we're actually going to have you guys do the exercise of walking through, following through a study from the design component. I'll walk you through, and then Martijn will walk you through actually the R code, and you guys can work along. Just a show of hands here. How many people have R actively installed on their computers? Everybody. Wow, that's cool. How many people already have the cohort method installed on their computers? Pretty good. That's actually better than I was expecting. That's really cool. Okay. How many of you have access to a OMOP Common Data Model instance that you can connect to from here? That's actually pretty good too. Okay. Yes. Keep your hands up because other people need to look around. How many of you actually can connect to that from your laptop right now? Can connect to that database using R? Wow. Okay, that is spectacular. Okay, so that might influence how we play some games here today. Okay, so and everybody has a laptop, so you all should be able to. You're all on the Wi-Fi. It is Marriott Conference, and then it's OHDSI 2017. It's not working?
Lowercase.
All lowercase. All lowercase.
So it takes either.
What's that?
It takes either.
Oh, it takes either. No space between. OHDSI.
In the morning, if you're having technical issues installing R, the cohort package, getting online, I'm going to be floating around to just grab my attention. All right?
Okay. So we're going to basically talk you through everything, and then we're going to have you experience doing one together as a group. And then at the end of the day, we're actually going to have you work as groups to actually design your own study and work through that, and Marc will lead you through that. So we ready? Are we ready? Yes. All right, good. So, new user design. Hope you all heard yesterday, our mission is to improve health by empowering a community to collaboratively generate evidence that promotes better health decisions and better care. What we are going to be talking about today is a specific aspect of what we think is a way to get there. You heard yesterday worked examples of us doing clinical characterization, population level estimation, patient level prediction. Very specifically today, the course you are in, this is about population level estimation. What you're going to learn about are the methods that if you're interested in answering a safety surveillance question, like does a drug cause a side effect, the methods you're going to learn today are going to be useful for that. If you're interested in comparative effectiveness research, so is one medical intervention better or worse than another for some outcome, you're in the right class. If you're thinking that, wow, Jenna Reps just rocked that presentation yesterday, I want some of that, you're in the wrong class. That's tomorrow. But today, you're going to at least get to benefit from Marc and Martijn and Christophe and I talking about this specific aspect. Just show of hands, how many of you have done your own safety surveillance or comparative effectiveness research study in the past? About half of you. Okay. Very good. That's helpful. All right. So you heard me say yesterday that what we're trying to do is we're doing methodologic research, open source development, and clinical evidence generation as a community. And specifically, this course is going to try to walk you through all of these components. So we've done a lot of research in evaluation of methods, and we're going to be talking you through some of that, and Martijn has been leading a lot of that work. You're actually going to experience the open source development. You're going to actually see the tools and be able to use them yourself. But really, this is about enabling you all to answer real questions that matter to patients. So that's what our objective is. By the end of the day, you all can go home and start answering questions and generate evidence to improve health. So the way that we think conceptually about how we want to follow evidence generation dissemination broadly, but very specifically here for population level effect estimation, is that there is a design component and a standardized implementation component. And I want to walk you through the steps of thinking about how we're going to come up with a question, review, and design a study. We want to publish protocols because the protocol is the document that should provide a complete specification of what you intend to do. And from there, we want to then, once you have a protocol in place, we want to walk through the steps of executing, evaluating, and synthesizing the evidence that's been generated. So we're going to walk you through how we think about these processes and what tools we've built to enable this. What's important here is, as a community, we're trying to help along this entire workflow here. So the questions that you might have, you can actually ask those questions to the community, and we can engage together with you. We have tools that will support both the design and the implementation of this, and we've got packages in R that are actually going to be able to allow you to execute these studies. And ultimately, we want these to be global network studies like you heard about yesterday. All right, so we're going to specifically today be talking about a comparative analysis. And to do this, I need to help you all think about counterfactual reasoning, or at least provide you a frame of reference. How many people recognize that picture there? So that is Keanu Reeves as Neo from The Matrix. How many people have seen the movie The Matrix? Most everybody. Okay. So that's great. So you remember that there was this scene near the start of The Matrix where Neo was offered the opportunity to either take a red pill or a blue pill. And at that moment, he was told that if he took one, that his life would be changed forever. He would go into the Matrix and have a experience that would change his life. And if he took the other one, everything would go back to normal, and we would and he would never remember what's going on. And so you might remember that he was given this option of the blue pill or the red pill. And ultimately in the movie, he chooses the red pill, and you watch the rest of the movie. And so you see what happens in his life based on the fact that he made a decision. He made a choice of taking the red pill. But the thing is, he was told this option. He was given this option between a red pill and a blue pill, and he chose the red pill, and you saw what happened because he chose the red pill. But you don't actually know what would have happened had he taken the blue pill. I mean, maybe he took the blue pill and they would have just said, gotcha, you're coming in the Matrix anyway. Or maybe it would have had no effect, or maybe it would have had some serious side effect, like angioedema. The point is that everybody makes decisions at a moment in time. Those decisions are not arbitrary, they're not random, and those decisions have effects. What we're trying to do is to understand and how to evaluate what is the magnitude of an effect. So what we would like to know is if he's given this option between a red pill and a blue pill, we think that there might be a difference between those two options. So what we're trying to quantify is, okay, given that he took the red pill, what happens? And what would have happened had he gone back to that moment in life and took the blue pill and seen what happened? each of you in front of you has a red pill and a blue pill. One of those choices for you is going to change your life forever. The other one is going to do nothing. I want you all to look down at your red pill and blue pill, and I want you to make a choice right now. Don't swallow, just make a choice. Has everybody made their choice? I now want you to swallow your red pill or your blue pill.
Y'all feeling all right? Just wait.
All right. If you swallowed the red pill, please stand up. Okay. I want you to look around, see who's a red pill swallower. All right. Why'd you choose the red pill? Melanie, why'd you choose the red pill? All right. Andrew, why'd you choose the red pill? Okay. All right. Mark, why'd you choose the red pill? Tastes better. Okay. Okay. So all of you guys had some reason for choosing the red pill? Your choice was derived of you. Okay. For all those of you that did have the choice, you had a reason why you chose the red pill. What's that? Somebody. And how did you randomly choose? It was closest. Okay, proximity. Okay, that's fair. All right, you guys can sit down. If you had a blue pill, stand up. All right, definitely a little leaning to the right on this. Okay, so why'd you choose the blue pill? Sergio, why'd you choose the blue pill? Matches the shirt. Okay, that's a good reason. Evan, why'd you choose the blue pill?
I know my flavors are jelly bellies.
But that's interesting. Your choice was taste better, but we all heard another person say their choice was taste better. So the same attribute, taste better, made you guys make alternative choices. Okay? In the back, why'd you guys choose the blue pill?
I just like the blue color. That's my favorite
Color?
color.
Okay. Okay. So you had reasons for choosing the blue pill. I want you to look at each other. Who's our blue pill people? All right. All right, and you guys can sit down. So remember your color. One of those is going to change your life forever, and the other one might not. There's reasons why you made a choice. And the issue that we're going to try to expose as we talk throughout today is how do we actually quantify the choice that you made and understand what would have happened had you not made that choice. So when the particular one that we did something special to impacts you, remember that. All right, so I want to try to drill down here on this idea of the counterfactual reasoning. Think about a person who's going along their lives, and at a moment in time, they are given this choice, the choice that you just made between a red pill and a blue pill. They make that choice, and then they go on with their life. They go on having made the choice of a red pill. And then they experience some sort of an outcome. We're looking for the effect of having that particular treatment. What you'd really need to do, if we could, is we would jump in the Delorean and go back in time to that exact moment when the red pill and the blue pill choice was made, that moment you just experienced 2 minutes ago, and force you to make the alternative choice, to make you take the blue pill instead of the red pill or the red pill instead of the blue pill, and then watch your life move forward from that moment in time to see if there's some different outcome. What we would want to do is have a Delorean, and then we could actually do counterfactual reasoning just fine, because we would be able to see what happens to you with the red pill, what happens to you with the blue pill, and we could just compare those alternative outcomes. In this construct, that decision represents an index point. It represents a moment in time when a decision's made. And what we are going to be talking about a lot is what do we know about a patient's journey before that moment in time? And then what can we observe following that moment of the decision? And this is actually quite important, and as you're thinking about the papers you've read and other research, sometimes it's difficult to figure out what is actually that moment that they chose the red pill or the blue pill. But that's a key moment, because we are going to be looking at what happened before you made that choice and then looking at what outcomes are experienced after that choice. So if we had a population, not just one person, but a whole population, you'd have a lot of people who were basically making decisions at some moment in time, and there would be a series of outcomes. So it wouldn't just be one person, but it would be a whole series of people. And you'd like to get a Delorean for each one of them, have them all go back, and then we would have a population type of understanding of what was the experience for people on the red pill and what was the experience for those same exact people had they taken the blue pill. And in that particular context, you would now have a cohort of red people, and the same people would be a cohort of blue people, and you'd just be able to compare the outcomes directly. That's what we would want to be able to do. But we don't have a Delorean yet. So what is our next best approximation? What could we do given that we don't have a Delorean? Well, instead of studying the same population under both decisions, maybe we could define a larger population and randomly assign people to one treatment to each person, and then compare the outcomes of the two different cohorts. So what that would look like is you'd have a whole bunch of different people, and you could basically, we could have told you that you are a red person and you are a blue person, and then we could just hope that those groups of people were sufficiently similar, and we could compare what was assigned and just what's not observed, that counterfactual that we couldn't see. We're just going to hope that that takes care of itself. This is fundamentally the idea behind a randomized trial, and this is actually proves to be pretty good on expectation to work for approximating what we really want to do. Reason I'm harping on this very basic is often you'll hear people say, well, I'm trying to design an observational study that approximates a clinical trial, and that's wrong, because a clinical trial isn't actually what we want either. A clinical trial is an approximation of what we really want, which is this counterfactual rationale. So when we say we're trying to approximate something, what we're really trying to do is come up with a design that's going to approximate this counterfactual thinking. So in this particular case, randomization is going to take different people who are assigned different choices, but you're going to hope that on average those groups are sufficiently comparable. And that works pretty well. But we're all here because we're part of an observational data community, so we can't even do randomization. So what's our next best approximation? And there are lots of different study designs that have been considered and proposed and implemented, but fundamentally we can kind of break this down into two real choices. We could define a larger population and observe the treatment choices were made and then compare outcomes either between persons who've made different choices. That's what we're going to talk about today with a comparative cohort design. Or within persons, you made a choice of the red. Maybe later in your life you could make a choice of a blue, and we could compare your different experiences at different moments in time. That's fundamentally what we think about in terms of self-controlled designs. So these are both viable and reasonable designs. Today's course is going to focus on comparative cohort design as one approach to this approximation. It's just because that's the course that we're teaching. We also have tools and processes for those self-controlled designs, and we're not advocating that this thing we're going to teach you today is the right way. It's just one way to think about this problem. So I had fun going through all of my old epidemiology textbooks because I thought it must be pretty straightforward to just define a comparative cohort study. You can just grab any textbook and you're going to find a definition. And it turns out that yes, you grab any epidemiology textbook and you're going to find a definition of a cohort design. And that became extremely problematic. I want to read you how my epidemiology textbooks actually talked about this. So Kelsey et al. Said, in a retrospective cohort study, the investigator identified the cohort of individuals based on their characteristics in the past, and then they reconstruct their subsequent disease experience up to some defined point in the most recent past or up to the present time. So just show of hands, how many people does that definition resonate with? Like when you think of a cohort design, does that sound good? A couple hands, maybe. Okay. Well, that's what Kelsey et al. Said. How many people have a Fletcher-Wagner epi book? Andrew does. Marc does. Okay. So in this book, they define, in a cohort study, a group of people, a cohort, is assembled, none of whom have experienced the outcome of interest, but all of whom could experience it. And on entry to the study, people in the cohort are classified according to those characteristics, e.g. possible risk factors, that may be related to the outcome. These people are then observed over time to see which of them experience the outcome. So this is this notion that there's like a cohort, and then you're just going to assign, or you're going to observe what those people were and classify them based on what you observed. So how many does that idea resonate with? A few more hands are feeling kind of good about that. Okay. Zlaslow and Nieto, they defined the cohort study as most representative format. A defined population is identified. Its subjects are classified according to exposure status, and the incidence of disease or any health outcome of interest is ascertained and compared across exposure categories. How many people like that definition? Okay, a couple more hands on that one. Okay. If you read Brian Strom's textbook on pharmacoepidemiology, it talks about that cohort studies are studies that identify subsets of a defined population and follow them over time, looking for differences in their outcome. Cohort studies are generally compared exposed patients to unexposed patients, although they can be used to compare one exposure to another. So that is the definition you'll find in Brian Strom's textbook. So how many does that resonate with? Only a couple. So you'll notice a distinction here is this one's actually talking about the design in terms of cohorts, plural, multiple groups that you're then comparing, as opposed to those other definitions we're really talking about there was a cohort and then you were somehow classifying individuals. Ken Rothman's textbook says in the cohort study, the investigator defines 2 or more groups of people that are free of disease and that differ according to the extent of their exposure to potential cause of disease. Their groups are referred to as study cohorts, plural. When 2 groups are studied, one is usually thought of as the exposed or index cohort, those individuals who experience the putative causal effect or condition, and the other is then thought of as the unexposed or reference cohort. So this is the Rothman definition. How many does that resonate with? A few more hands. Okay. So how many of you, none of these resonated? So what I was actually quite struck by when I was doing this, putting this together and reviewing this, is that as a community, we are using very different language to describe the same kind of construct. And so what I really want to do, what we want to do today is provide you a common language. It may or may not be what you want to think about, but it's going to be a common language that we're going to use to describe things, because what we find is there's a big distinction if you think about the world as one cohort and you're just subsetting, versus think about the world as 2 cohorts that you are comparing. So we are going to provide you a common reference and a way to think about this, and we'd love to get your feedback if it resonates with you by the end of the class. But a lot of what our focus is going to be is just to standardize the way that you think about this structure. So and we're largely going to be kind of following this, the Rothman kind of framework. We're going to hear us talking about 2 cohorts that we're going to compare against each other. So effectively what we're doing is we've got different groups of people. Some made the choice, like in this room, some of you chose the red, and some of you chose the blue. And we're comparing those 2 cohorts, those individuals, to observe what happens to them and to make comparisons. The challenge that we have is the reasons why you chose the red and the reasons why you chose the blue matter. And it could actually be that there's some fundamental difference between those of you that chose the red and those of you that chose the blue. So even if you did observe a difference in the outcomes that were experienced in those 2 groups, you don't know whether it's attributable to the actual choice of red or blue, or whether it's actually attributable to the fact that those groups of people are just fundamentally different. So there's an exchangeability assumption that can be violated that allows that complicates how we're trying to evaluate treatment choice when you have some other effect that could be going on, which is just the population differences. Does anybody remember what these little icons are coming from? Who's that? Ice hockey. We got one ice hockey. What's that? So this is an original Nintendo Mario game. It was ice hockey. And the thing was, when you played this game, everybody actually made an explicit choice of the team they were, and everyone who ever played this. So what was your favorite lineup when you were growing up playing this?
Like 2 skinnies, 1 big, and a medium.
Yeah, so I was 3 skinnies and a fat. So so everybody knew their lineup because you made a defined choice that you made. And so it's not just a matter of if we were going to play, we play it 10 times. It's not a random choice. I'm always going to make the same choice. You're always going to make the same choice, and I'm going to beat you because 3 skinnies and a fat's way better than having a medium. So you've probably heard about propensity scoring. Actually, how many of you have heard about propensity scoring? Excellent. How many of you use propensity scoring? Many of you. Okay, good. So I'm going to breeze through this then. So propensity score is the ability, it is the construct that we can use to try to account for the fact that these groups might be different. And it's one of many strategies that you can apply. Effectively, what we're trying to do is estimate the probability of treatment assignment based on your baseline characteristics. So that decision point that we had, that moment that you made the red or blue pill, we're going to use all of the information we have about you up to that moment in time to try to predict who chose the red and who chose the blue. So if we could use your baseline history, we're going to fit a predictive model to try to figure out what treatment choice you've made. On the basis of that predictive model, we can then use that information to try to balance the two populations, effectively trying to make the groups as similar as possible based on their likelihood that they would have chosen the red pill or chosen the blue pill. So the general intuition about this is that if we could have in this room, those of you who chose the red and those of you who choose the blue, if we could have learned everything about you up to that moment and fit a model, we might have been able to figure out who amongst you was likely to choose red, who was likely to choose blue, and we could have seen that some of you might have been likely to choose red but actually chose blue. And some of you might have actually chosen blue but would have been likely to choose red. We can use that information to basically try to find someone is similar to you on the basis of what their likelihood of having that choice to be. And what specifically we're going to go through is various strategies that you can make use of this propensity score construct to try to make groups as similar and evaluate whether or not you've actually gotten close to that counterfactual that we're trying to achieve. So there's lots of reasons to use. Since everybody raised their hand, I'm going to probably skip through a lot of the details here. But the main point is that we want to highlight is we're going to show you how to implement large-scale propensity scoring. That is just one of many strategies to get around this counterfactual thing. But we are going to show you some diagnostics that are going to help you understand, is it actually working for the purpose we have, which is to try to approximate that counterfactual statement. Once you have an estimate of a propensity score, which is this predictive model, you have to then make use of it. And there's various strategies that have been used in the community to make use of a propensity score to try to make groups similar. So for example, you can, some people will put it into an outcome model as a regressor. Some people will do matching, stratification, inverse probability weighting. Other people are trying lots of things. I'm just curious, show of hands, how many people here, those of you that said you're using propensity, how many people here do matching? Okay, how many do stratification? A couple other hands. How many people are doing inverse probability treatment weighting? A few hands. How many people are doing regression, just adjustment? A couple hands. Okay. So there's diversity of choices that you get to make as part of this design thing. At this point, it's generally been not recommended to only do regression adjustment, and there's details that we can provide if anybody is interested in that. For purposes of what we're going to be talking about today, you're going to see examples of how you can do matching and stratification, and so we're going to focus on that, but that's not because we don't think that inverse probability weighting is not an option. It's just that that's not where we're going to focus our energy today. So effectively, what matching would actually look like as a strategy is you've got your green people and your red people, and you're trying to match them. What we're going to do is look for the common characteristics. And we're going to find those people that look similar but made an alternative treatment choice. And we're going to restrict our population only to those matched populations. Once we have those matched populations, we'll then be able to compare the outcomes for them. Stratification, on the other hand, is that we're going to split the population based off of their baseline characteristics. So maybe we will split into small, medium, large in this particular case. And then within each strata, we're going to be able to compare populations and see, is there a strata-specific effect? And then we can pool those strata-specific effects together to get an overall treatment effect. So in some of our prior work, we've published about the new user cohort design and evaluated its performance for the purposes of safety surveillance. And those of you who went and checked out Martijn's posters yesterday, you also saw a pretty large-scale evaluation we've now conducted for comparative effectiveness research. And I want to just make this point very, very clear that we are giving you a tutorial on how to do this method, but we are not telling you that this method is perfect, that this method will get you the right answer. In fact, if anybody reads our paper, you're wondering why are we giving this tutorial at all, because what we've shown is actually this method can get good answers, but it is very, very, very easy to get really, really, really bad answers. And we've now shown over the course of 5 or 6 experiments that while everyone's out there saying, well, if I just do a new user design, I'll be fine, that there are lots of ways that we could actually generate invalid estimates using this approach. So you have to be very careful about thinking that. And so what we've been focused on as a community as we've been developing methods, how do we create a standard framework with defined choices so that we can be explicit and transparent about how to conduct a study, not necessarily guaranteeing that we're going to get a valid estimate, but at least guaranteeing that, one, we can be transparent about what we did, and two, we can actually show and formally evaluate to demonstrate whether or not the method looks like it's generating valid estimates. So this is where I'm going to try to provide some common language, and we'll love to get feedback of whether this works for you or not. In OHDSI, we have a definition of what a cohort is. A cohort is a set of persons who satisfy one or more inclusion criteria for a duration of time. So I want to just think about that for just a second. You got people who have membership at some time. That there's consequences about this. So one person could belong to multiple cohorts, because if you have different criteria, one person could belong to many different cohorts. One person could belong to the same cohort at multiple different time periods. You could enter a cohort, exit that cohort, rejoin that cohort. However, one person cannot be in the same cohort multiple times during the same time period. Effectively, at any moment in time, you're either in or you're out, and we define those durations of time to sort that through. One cohort can have 0 or more members. It's actually perfectly possible to have a cohort definition that is well defined. It just is that there are no people who satisfy the criteria in your population. So for example, if I'm interested in a study of new users of a drug that's primarily used in the elderly, that might be an Alzheimer's drug, a new users of an Alzheimer's drug. That might be a very well-defined cohort, and it's going to work great. And then I'm going to send it to Hanya, who's at CHOP, and there's no kids that are going to take that drug. That doesn't mean that we don't have a perfectly specified study. It just means that her data doesn't have membership to that cohort. One last thing, and this is just Patrick's personal pet peeve, so just watch yourself when you ask for questions later. A code set is not a cohort. I get so perturbed when I read a paper that says the cohort was defined as 250 star. 250 is an ICD-9 code for diabetes. A code is not a cohort. What you need to be able to say is, I'm finding people who have one or more codes for some period of time. That's a well-specified definition. But a code set by itself, 250 star, that is not a cohort definition. You have to provide the logic. And all too often, and as you're going through the examples today, I want you to be thinking about this, is how explicit is the logic for defining the cohort membership actually being expressed? You're going to learn today about using Atlas as a tool, and this is just one of many ways you could do this. We care a lot as a community about this kind of idea that we have standardized ways to think about things. We are agnostic to what tools you're going to use, but we are going to show you how to do this in Atlas. And inside of Atlas, we formally define a cohort by having a cohort entry criteria, which is basically how did you first have some initial qualifying event that occurred that you're going to make use of. You can then specify qualifying inclusion criteria, which are basically further ways to restrict that subset of people out. And then there'll be a cohort exit criteria, which is basically when you leave the cohort now that you've entered it. We will be showing you in the tool how this actually works, but we want to be thinking from the perspective of what did it take for you to have that decision point, that moment that you entered? What specific subset are you going to be filtering down to? And when, for that subset you have identified, would you actually leave that cohort? So if you've got an OMOP common data model, you've got a population of people with lots of observations, and we can define lots of different cohorts under this framework. You might be thinking about a new users of a drug. You might have lots of different drugs in your database. You might have people who have a surgery, people who have taken multiple drugs concomitantly, people with a condition, people with a device, people who had an outcome. These are all cohorts that can be manifest and represented in your population. Now, the framework that we're going to be talking about for the comparative cohort analysis basically is going to get distilled down into these 5 decision points that we think we can properly define most comparative effectiveness studies based only on this. And you're going to hear us beat this over and over throughout the day. There's a target cohort. That target cohort represents the exposure of interest that you're interested in studying. So new users of a drug, new users of some sort of an intervention. For that target cohort, you want to have a perfectly well-specified cohort definition. people who satisfy inclusion criteria for duration of time. And it's usually going to be that cohort entry, which represents that moment when you're in this target cohort T population. We're going to create a second cohort called a comparator cohort, or C. This is going to be the group that you're going to use to compare your target to. It could be people on some alternative treatment or some other population that you're defining, but it needs to satisfy the exact same cohort definition of a set of people satisfying criteria for a duration of time. We're then going to have you define a third cohort, which is the outcome cohort. Now, this is something that sometimes is not immediately intuitive, but an outcome, if we're going to look at the Graham study, we're going to talk about comparing warfarin with an outcome of GI bleeding. The GI bleeding outcome, very often when you're reading papers, people just talk about, amongst my people, I looked for an event to occur. But in fact, you could reframe that problem to say, who is the cohort of individuals who have GI bleeds? And that is actually a well-specified cohort definition, a set of people who satisfy criteria for a duration of time. Effectively, you're saying, when did the GI bleed occur? We have created this framework whereby the outcome definition is defined independently from either the target or comparator group. So you're going to define 3 different cohorts. And I think throughout the day, you'll hopefully get a sense of why this will be useful. So rather than thinking about, you've got a population and we're going to create some sort of like indicator flag in the data of yes, no, they had the outcome. Instead, think about this as you are defining 3 different populations. With these 3 cohorts in place, you're then going to be making model specification choices. The first choice you have to make is the time at risk. So what is the duration of time that we're going to look to see whether or not the outcome was experienced amongst either the target or the comparator cohort? So that time at risk is a choice that we have to make, and it actually is part of the fundamental question specification. And then the last thing that we're going to work on is how to actually specify a model. So how do you specify the statistical algorithm that you're going to apply to your T, your C, and your O for that time at risk to be able to generate some sort of a causal estimate? So this table is something that we want you to be thinking about. You're going to be using this as a rubric to think about how to interpret papers. You're going to be using this as a rubric to walk through your studies. And as you guys are thinking about your own studies, I really encourage you to be thinking about how does the study that you want to answer when you go back home, how could it fit in this framework? So you're going to hear throughout the day that we're going to keep harping on what's your T, what's your C, what's your O. In a comparative cohort analysis, because we have some target cohort, the population that we are interested in studying, there's going to be some subset of them that are going to be appropriate for allowing this causal inference analysis to be done. And partially that's because not everybody in the cohort might be applicable for the question of interest. Take, for example, if we are going to make a comparison between a target cohort and a comparator cohort, there are people that actually might be in both of those cohorts at the same time. And so if we're interested in trying to understand what is the effect of T versus C, having someone who's on T and C greatly complicates that. And so we have to make choices about what to do in those circumstances. So what you're going to see as we walk through the process is that you're going to start by defining your target population, your comparator population. But then as we conduct the analysis, we're going to end up subsetting that to the analytic target population, target cohort, which is going to be the subset of people that are actually used for the causal inference, and that analytic comparator cohort, which is the subset of people that are going to be used from the comparator. And we're hoping to use those analytic cohorts to generalize to the original target populations that you were interested in. You then independently are going to have your outcome cohort, and fundamentally the questions that we're asking is, in your target, in this analytic target cohort here, there's some subset of those people who had an outcome during a time at risk. You've got an analytic comparator cohort here. Some subset of those people had an outcome during the time at risk. And that's the comparison we're going to try to draw. So target cohort, comparator cohort, outcome cohort, then you have a time at risk. The last thing that I mentioned was a model specification. You've got choices to make about what kind of model you're going to do. And fundamentally, the choice of your outcome model defines what the research question it is that you're actually going to be answering. Within the tools, we're going to focus on 3 different design options that kind of cover a lion's share of what we see happening actively in the literature. you have the option to use a logistic regression, a Poisson regression, or a Cox proportional hazards model. We want to walk you through these different choices and what they actually mean in terms of defining your research question. So for a logistic regression, you're actually you're doing a binary classifier of the presence or absence of an outcome during a fixed time at risk period. So if you're interested in answering a question of comparing some target group versus some comparator group and whether or not those groups just have an outright difference in the presence of some outcome, a logistic regression can work and you get some sort of an output, which would be an odds ratio. The challenge here is that every person has a fixed defined time period because you only have the information about whether or not that outcome was experienced. Another option that we can use is a Poisson regression. And here, instead of it being about the absence or presence of event, you can actually count the number of occurrences of event. And here, instead of thinking about an odds ratio, you'd actually be getting a rate ratio because you're actually looking at the differences in rates between how many outcomes are occurred. This makes an assumption that outcomes are following a Poisson distribution and that you have constant risk over your time period. And that assumption can be a challenge. The third option here is a Cox proportional hazard model. And here is where we're trying to compute a time to event relationship to understand in your time at risk horizon from the start to the end, what is the earliest time of occurrence of an event. Here the output of this would be a hazard ratio. And there is an assumption that's made here, which is a proportionality assumption that also needs to be tested and assessed. The key here is that you can decouple the model specification from the definition of what your target, your comparator, and your outcome cohort is, as well as your time at risk. But by making this choice of what model you're using, it's defining your research question. All too often what we see is, what I see when I'm reading the literature is people will have a very well specified research question, but then you have to keep scanning the literature and eventually get to the method section, and then you see what model they chose. And not always is it the case that the model that they chose matches the research question they asked. But these things are not just tightly coupled, they should be one and the same. And in fact, as you'll see in our tool, we will write your research question for you once you make the choice of the model. Flipping that around. So I mentioned earlier, when you design an observational study, some people will say, well, what I'm really trying to do is I'm just trying to approximate the experience of a randomized clinical trial. And I'd say, no, we're actually trying to learn that counterfactual effect. However, a lot of the design principles that go into designing a randomized trial are very helpful and appropriate when you're thinking about designing an observational cohort study. So key components that go into a protocol are things like the eligibility criteria. What are the treatment strategies? What are the assignment procedures, the follow-up period, the outcome, the causal contrast, the analysis event? This is the things that go into a proper design of a randomized trial and can go into an observational study. This actually matches up exactly with the framework that we're going to try to show you, just trying to put it in very specific language that will actually make sense for both designing a study and then ultimately implementing it. So this standardized process, we really are going to be trying to help you understand and split between the design components up front and then the implementation components. And that step in between is publishing a protocol. We want to have a full specification, a complete specification of every choice you have to make in this design such that you can, that anybody should be able to fully reproduce the study if they wanted to. So starting with the research question of interest is what question is actually being asked. We want to understand what's the motivation for asking that question and what decision is the evidence trying to inform. So are you trying to estimate a relative effect or are you trying to estimate an absolute effect? Are you asking a drug safety question where the question might be, does the drug cause a side effect? Or are you asking a comparative effectiveness question, which is, does a drug cause an effect more than some alternative treatment? It's very easy to get those questions confused. And particularly as we're going to talk about a comparative cohort design, you are going to be making a comparison between a target cohort and a comparator cohort. Sometimes, if you know that the comparator cohort is just serving as a proxy for the counterfactual, that is, it has no effect on the outcome, then you might be trying to draw an inference about an absolute effect. Very often, though, you don't know what the effect of that alternative treatment is, in which case you are making a comparative assessment. And sometimes you will see, maybe even in some of the examples you've read for the class, sometimes you'll see where these lines get a little bit blurred. When we talk about review, it's important that any new evidence that we're generating is just one extra piece of evidence, and you want to understand what evidence actually already exists out there in the literature or in medical knowledge, and what is the evidence gap that we're actually trying to fill. It's pretty easy to come up with questions. It's a lot harder to know, if I do this question and generate this information, how is it going to situate with everything else? And we think it's really important that up front you think about that. For those of you, so one way to think about this formally is from the perspective of Bayesian thinking. There's a prior belief of what is known about a particular question. We are going to generate new information to try to produce some sort of posterior thinking about what's going on. If you don't start your study by first knowing what's your prior, then when you generate information, you don't know how that information can be informative. It's just another piece of data. So it's important for you to think about this up front. In terms of the design, we are going to be walking you through how to actually make all of these design choices. There's been some confusion amongst people who have been watching OHDSI from the outside, that because we are developing standardized processes, somehow we're trying to automate or remove manual human thinking from design choices. Quite the contrary, what we're trying to do is create a consistent framework to help think through what the design choices are, but these are still choices that you as researchers have to make. What we want to be able to do is evaluate those choices in a standardized way. But fundamentally, your research question really does require some domain expertise to figure out what choices are appropriate. One thing that we've seen is inconsistently applied across the broader research community is the idea that protocols should be generated, documented, and published and made publicly available. OHDSI has provided a resource so that you can now do that. But even if you don't want to share your protocol with the world through OHDSI, we think it's really important to have a protocol, and that protocol needs to be a complete specification of every design decision that's made up front. This is often hard, and often it's easy to get into the point of you write down a conceptual protocol of this is broadly what I'm going to do, but it really should be a document that you actually could hand to anybody, and someone else should be able to independently execute your study if that protocol is properly specified. Once that document is over, it could be handed to anybody, or it might be yourself doing the study. You should be able to execute that study. We're going to be showing you standardized tools to do this. Standardized tools should have a common defined set of inputs, a TCO, time at risk and model specification, but it should also have a standardized set of outputs. And so Martijn and Marc have been leading the efforts to try to figure out what are those best practices of outputs that we want. We want to show you what the tool is doing, but we also want community feedback to figure out what other things should analyses be generating. The key here is that the specification up front in the protocol should simply be executed end to end to generate all of the output. There should be no need for a person to be manually intervening and navigating through the data if you are properly designing your study up front. Once you have results executed, you need to evaluate and interpret the results that are coming out. One of the things that we're harping quite a lot on is that evaluation is something that we think the community needs to further expand best practices. Statistical methods will spit out numbers. You're going to get a whole bunch of numbers, and you can interpret those numbers. But the question is, to what extent can you trust those numbers? When you get a 95% confidence interval, can you actually trust that the truth is in there 95% of the time? If you get a p-value that's less than 0.05, does that mean you had 5% random chance? What we have developed is a series of diagnostics that are at least going to help you understand some of the issues about whether or not the result you've generated is trustworthy, and Martijn will walk through all of that. And then synthesizing the evidence you've generated means that you need to put it into context with what else has been known. So the reason we really think that it's important for you to have that prior belief is because you want to understand, now that you've executed the study, how have you revised your understanding of the problem to provide new context. So Yitzhak had looked through the literature about alendronate and raloxifene, but there was a gap in the evidence. But now that we have this new piece of evidence, the question is, how do we inform and move forward with this new piece of information in context of what we already knew? What we think needs to be done throughout the broader research community is that all of these steps should be able to be followed in a pretty succinct and efficient way. But we should also be able to standardize how we represent this information. And if you are interested in publishing your work, as Marc certainly is, one of the useful aspects is that if you do your review, that is your background section. If you do appropriate protocol, you have now actually written the methods section of your manuscript. The execution is going to generate directly the results that just make up your results section. And your synthesis really represents the discussion of how you're putting this information in context. So you should be thinking, when you have a design idea, an idea of a question, how do we actually take that all the way through disseminating the information? And we're trying to provide a consistent framework to get there. So when you are designing your study, when you are reviewing someone else's study, when you're reading a paper, we want you to be asking yourself, what's the target cohort? What's the comparator cohort? What's the outcome cohort? What's the time at risk? And what's the model specification? If you leave with only one thing today, it would be that you're going to be asking for what's my T, what's my C, what's my O. And if you can do that, we think that you're actually going to get a long way towards being able to design and execute a study. And we're able to walk you through the rest of that today. So let me stop there. And I know that was a lot of long-winded talking there. So let's stop and have a quick discussion. Any questions, comments, reactions? Yes, Scott.
The propensity score discussion,
Yep.
and then this discussion here, can you connect those?
Sure. So when we talk about model specification, what we're talking about is what is the statistical strategy that you're taking to produce the estimate from these populations. So in that model specification, and you'll see through the tools, that's actually going to be where you make the design choice. Do you want to use propensity score as a strategy? If you do you want to do matching or stratification? Are you going to apply that prior to actually executing your outcome model, being a logistic regression or a Poisson or a Cox proportional, or is it actually going to be part of that model? So you're going to be making a series of model specification choices about how to make the groups comparable and what outcome you're going to be producing. So
Propensity score helps you go from the initial down to the end.
That's
It's
right.
one of the ways.
That's one way you can use it, absolutely. Yep.
That's good. And then second, real quick,
All right. Any other questions?
You mentioned the Poisson regression. I wonder, are you talking about the Poisson itself or Poisson family? Something like an aggregate and
Specifically here, we're actually talking about a Poisson regression, very specifically. When you use, slightly tangential to your question, but when you are using, so we're going to show you how to implement a family of regression models that have been developed by Marc and his team to do large-scale modeling. In each of those cases, you could either be doing a conditional or an unconditioned version of a logistic regression, a Poisson regression, or a Cox model. So those are the design choices that you're going to be making. Yep. Yes?
So with the propensity scoring, you can really throw in a whole bunch of variables and kind of let it run through a very reproducible process. Some other types of analyses, we find that human interpretation of the variables, correlation structure among variables, for instance, where a regression model, you can't have both variables, and a human being has to kind of think about the meaning of why some problems come up. I mean, I'm wondering how you think of trying to pre-specify the troubleshooting that goes on in studies. You find a covariate, you design, there's nothing there, stuff like that. How would you avoid having to do any of that after you've read the stop sign?
It's a good question. So we're going to go into more depth about the propensity score as we actually walk through the studies that you're going to go through and some of the examples. But I guess just to give a brief teaser about this, one of the things that when reading the literature, it's not immediately obvious, but I want to tie this back to something you heard yesterday. A propensity score is actually purely just a predictive model. So it's actually akin to what Nigam Shah was presenting and what Janet Reps presented yesterday. It's a prediction model. You are predicting whether you took the red pill or the blue pill. If you heard both Nigam and Jenna's talk when they were talking about prediction, they both made a very important point, which is prediction is not about explanation. It's not about saying that you know why you are producing a prediction. It's about maximizing your predictive accuracy. In that context, if you think of your propensity score as a predictive model, our goal is to predict treatment assignment as best we can. That is the objective of that task. The reason is because we're trying to approximate that counterfactual reasoning, going all the way back to, can we get that person to be the same exact person except for their treatment choice? This is something that in the literature there's quite a lot of active discussion. It used, actually, since many of you are doing propensity scores, for those of you who do propensity scores, how many of you generally make clinical decisions of what covariates go into your model, into your propensity score model? Only a few, okay. So when you do that, when you're making those manual choices, how many variables will you put in?
I was just going to say, I think it depends what type of model you use, because if you're just going to use like just regression, you may just think of the X model, you have a lot of functional forms that you have to think about. But if you use something else like a random forest or whatever, that model will help sort of define, figure out whatever that functional form is and include interactions and those sorts of things for you. So depending on what you use, you probably should compare different types of models.
Yeah, so I'm just curious, in the back of the room, can you hear the comments? Yep. No? Okay. So I want to restate this because I think it's actually an important point. The comments made, it somewhat depends on the model you're going to use to fit your propensity score. I would guess, well, at least from the reading I have done, I would say that over 95% of papers say they're doing a propensity score, and it's implicit that they are doing a logistic regression. And it's a logistic regression with only main effects variables, and that's just what people do. But in fact, if I tell you it's just a prediction model, then that means any predictive modeling algorithm could be used, whether that be a regression or a random forest or deep learning or whatever you want to do. The goal is to estimate that probability of treatment assignment. Yes?
So one related thing, as you get into doing more deep learning, you do have to have some sense of the relatedness or do some adjustment for the a priori of the relatedness, because the machine cheats and then you have an AUC that's just completely unbelievable,
Yep.
right? But
So with every predictive model, you have to think about how you want to evaluate that model and assess its validity both internally and externally. And so one of the challenges that you run into is that, one of the challenges that I see in the literature is because we don't think of a propensity score as a prediction model, we just think of it as this confounding adjustment strategy that people are doing in inference, that the best practices for prediction in terms of how one does a model evaluation, how does one check the diagnostics, are very, if they're being done, they're not being reported. And I suspect that they're actually not commonly being done.
Sorry, maybe this is the right time to ask. So one thing that we find in BA is that we have certain amounts of data, more on some people than other people.
Okay.
Is that actually rolled into a propensity score based on the fact that they just don't have those elements?
Yes.
Or do you need to separately do something to try and define how much exposure you actually have versus how much non-code you have for real reasons?
Yeah, it's a good question. I'm going to go back to Christophe's point with this. When you are fitting a model, you're going to try to make use of all the information you have at your disposal. Some people, like the few handful, think about that as, I will use my clinical expertise to make choices about a few dozen variables that they're going to put in. Other things, other strategies that are out there in the literature is people have developed ad hoc heuristics for how to go into the data and find a subset of variables. So, for example, Sebastian Schneeweiss published a paper on high-dimensional propensity scoring, which basically applies a univariate statistic to find 200 variables and then throw it into a logistic regression. What you're going to learn about today is how we can do large-scale propensity scoring using lasso regularized regression, whereby you can throw in as many variables as you want. Those variables can be things like the presence or absence of a given condition, drug, procedure measurement. It can also be things like the count of the density of data, so how much data do you have. Those are choices you get to make in terms of how you specify the model of what you want to put in. What you'll hear Martijn and I argue is, and hopefully you heard from Francois Morlaix, lots of decisions is a lot of arbitrary stuff. And so as much as possible, if we can actually be in the situation where we can let the computer make choices and get an objective, reproducible result, we think that that's useful. Thus far, and Yushi's working on a paper, we've been able to demonstrate that large-scale propensity scoring works really, really well, and it's fewer choices. So we can make fewer choices and get better performance. We think that that's a win all the way around. Yes?
It seems there's one arbitrary choice that should be made, though, with respect to propensity scores. Isn't that clinical or statistical, whatever the criteria you think about, is that you only want to include things that would precede or reflect the situation preceding the actual treatment or propensity, correct? That's got to be the human level right there.
That's a extremely important point, and I'd say it's not even a decision. To do this design appropriately, your propensity score has to be based off of covariates that precede the decision. End stop. You don't get the choice of looking in the future. You don't get the Delorean or the crystal ball to go forward.
Yeah, I just figured that should be made explicit.
Yes, very good point. Yes, yes. So you are going to be making use of the information before the decision, before you took your red pill, to try to understand what happens afterwards. And you don't get to mix those things. It's a really important point. I'm glad you raised it, because one of the things I see often when I'm reading papers is sometimes the lines get blurred, and sometimes you see information crossing those lines in ways that can actually confound a study.
I think it's related to that one, but I would like to hear people expand on it, because I just want to make sure my understanding is correct. So is what he's saying, for instance, I might create a propensity model around a clinical decision that winds up suggesting that a 20-year-old has the same propensity for a treatment as a 94-year-old, even though that just doesn't pass muster as a, that they may not reflect kind of the clinical reality that you'd ever kind of consider this treatment in a 94-year-old, despite what her other covariates are telling you in the propensity model. So how do you pull those out? Is that it sounds like it's related to that point, but how do you pull those out of a propensity approach?
Yeah, no, it's a fair point. So I think you'll get into a little bit when you talk about the propensity score diagnostics. But effectively, if you think of the task of a propensity score as just predicting, you want to know how well a prediction actually works. What you heard about yesterday in terms of validation strategies, I think those things should be getting applied to the propensity score. That doesn't necessarily help with the clinical interpretation of the fact that one person, based on their baseline history information, might look like they could have been given an alternative choice. You will see in some of the design choices, and there are some papers where people say there are regions of a propensity score distribution that you might think are not plausible, and you might want to actually trim them off. And that's a design choice that you get to make. But interpreting, like actually down at the patient level, this person, they seem to have a high predicted probability of getting a red pill, but in fact they got the blue pill. How did that happen? Those are really challenging things to think about. Sometimes you actually want to exploit that information. So you thought they were a red person, but they actually got the blue pill. Learning about why did that happen can actually be quite informative. But sometimes at an extreme, if you know a person's guaranteed to be a red pill all the time, then making a comparison between red and blue, that person's not really relevant to that causal contrast.
To follow up, and I think it may relate to what Christophe was asking about before, is there a point in the process where you can identify population characteristics which scream out for stratification in your analysis rather than inclusion of propensity score to try and make things equal? So if you, in this particular example, it makes no sense to be comparing people who are 20 and people who are 95, or a standard algorithmic way for coming up with that design choice about stratification. I guess it's another way of reframing.
That's a good way to reframe it. And I think what you'll see with Martijn's going through the results is we've put a lot of emphasis on the diagnostics that should be looked at throughout the study. And so when you see a diagnostic that tells you you should be concerned about a given study, the question is, what action are you going to take to rectify things? And there are choices to make in that. But if you're not looking at the diagnostics, you won't know that there's a problem. You'll just assume that there's not a problem. By forcing you to work your way through the diagnostics, hopefully you'll uncover, hey, there's some anomalous issue. I haven't resolved confounding, or I have imbalanced populations, and then you can think about what you're going to do about that, and you have choices at your disposal. Yes?
I was just going to say, in reference to what Scott was talking about, we're missing information in the game. That's important to think about that your propensity model, it only performs as well as the measured confounders that you have, and we still have this issue of unmeasured confounding. And the difference with the randomized control trial is that when you're randomizing, we think that that accounts for both measured and unmeasured confounding generally. Of course, you can never really know
Yeah.
about the unmeasured confounding.
Yes, we have in the afternoon. So we will discuss that in the afternoon. That's a good point.
And that's a limitation you have to put in.
Yeah, I didn't have to
observational
think about
study.
that right away moving forward and learning about it.
You could do sensitivity analysis, right? The degree of unmeasured confounding would change your results.
So the approach that we've developed in Odyssey is, I can give a big review, a preview is, we input a lot of control hypotheses. So in this case, we use control outcomes in our analysis, which are outcomes that are not believed to be caused. Well, we usually use negative controls where we believe that the outcome is neither caused by the target exposure or the comparator exposure, and therefore the contrast between the two should always give a hazard ratio or relative risk or odds ratio of 1. And then you can see whether or not you actually achieve that on your negative controls. And that is a way of measuring unmeasured confounding, because if there is unmeasured confounding in your analysis, you should see that on your negative controls. So
that's again a degree of belief there that there may be an unverifiable assumption that that is an adequate negative control, correct?
Yeah, so that's why we tend to use a lot of negative controls. So normally a paper will use 1 or 2 negative controls. We tend to use somewhere between 50 or 100.
Wow.
So that gives you more confidence that you're looking at the whole landscape, so to say.
All right. Matt, last question?
Yes. So I guess I'm just a little behind on some of the like statistical objects here. Is there somewhere I could just read a little bit, like you saying what a propensity score, the object of like probability of this thing given covariance? I understand what that is. I understand you can estimate it, evaluate it, et cetera. What do you do with those? Where can I kind of read just like the bare bones of that?
Yeah. So I think for the simple reading, I would suggest the paper that we published, which I'll just send you right now. You can take a look through it. We kind of just go through these design choices and how they get used in this various strategies. So I can send it out to the whole group, but that's just our, I don't remember if you were the lead author or I was for the cohort method one. One of us wrote a paper. So I'd reference that one just as the intro overview for that.
All right.
All right.